We want to start this video by asking you a question, and we want you to try to decide whether you think the statement is true or false. Do you think it's true that the sine of a sum of two inputs or two angles, like A and B, is equal to the sine of the first angle or input plus the sine of the second angle or input? Do you think that's always true? And I suppose what we might do is just take an example and try it. Now, if it works, that doesn't constitute a proof. To prove something like this, you'd need to show that it's true for any case. But suppose, let me just pick angles that are really nice to work with. Maybe angles that show up nice on our unit circle. So I'll let A be 30 degrees and I'll let B be 60 degrees. The question we're really asking here is the sine of 30 plus 60 degrees the same as the sine of 30 degrees plus the sine of 60 degrees? Now, I'm not going to pull up the unit circle here, but we actually know what this is. This would be sine of 90 degrees. Right? If you add 30 and 60, you would get 90. And I know what the sine of 90 degrees is. If I look on the unit circle, the sine of 90 degrees is 1. So the question would be, is that the same as what I'm going to get if I add sine of 30 and sine of 60? Well, the sine of 30 degrees, I can get that from my unit circle as well. That's a half. And the sine of 60 degrees shows up in the unit circle. That's square root of 3 over 2. And if I add these together, you know, it is convenient to add them because they have the same denominator. I would get 1 plus square root of 3 over 2. And I think we can safely say that no, that's not true. So in general, what we're trying to say is you can't simply, it's poor terminology, but you can't simply distribute the sine to both angles or inputs. There has to be a way to do it, though, and that's what we want to show you today. That's today's learning target. So strongly encourage that right now you pause the video and add these formulas to the back of your unit circle. If you don't like the way I've got them written here, they're also in page 377 of your book. But these are fair game on any assessment or test the rest of the year. So pause the video right now and copy these down. So it's important that we take a minute to show you truly what's written here and how to use it. Each of these lines here is really two formulas in one. Okay? We're saying that the sine of u plus or minus v is equal to the sine of u times the cosine of v plus or minus the cosine of u times the sine of v. So what we mean is that if you need to add two angles together, then you need to use the plus sign here. Or in other words, if you need the top sign here, you need the top sign here. If you need to subtract two angles, and you need the sign, well, you need to use the minus sign here. And actually, the other two formulas work that way as well. If you need a plus sign in the cosine formula, notice here that the signs are different. You need a minus sign. And if you need to subtract two angles and get the cosine, you need a plus sign here. But it all has to do with being consistent about which of the signs you picked. If you needed the top sign here, you need the top one here. And the same is true down here with the tangent formula, although we'll talk a little bit about the tangent formula in a second. If you need a sum of two angles, you need the top sign everywhere. If you need a difference of two angles, you need the bottom sign everywhere. This tangent formula is the formula for the tangent of a sum or difference of two angles, but I'm going to be honest with you, I very rarely use it if I need the tangent of an angle. And why? Well, to me, I think it's easier to use the sine and the cosine formulas, And then I know that tangent is sine divided by cosine. And I'll show you that in a second. So here's what we want to use these formulas for. We want to find the exact values of sine, cosine, and tangent of this angle, 165 degrees. So what I'm looking for in doing so, I'm going to use these formulas to do it, but I need to find two angles, like they'd be U and V, that show up on my unit circle, that either add or subtract to 165 degrees. And there are actually a lot of ways to do this, but the two that I spotted out would be that I could get 165 degrees by taking 120 degrees, which is on my unit circle, and adding to it 45 degrees. And there are other ways to do it too. You could use 135 and 30. They're on your unit circle also. So I'm going to think of those like my U and my V. Okay? So this is my mindset as I go about trying to find these values exactly. And now I'm just going to use the formulas like they're written. So if I need the sine of 120 degrees plus 45 degrees, all right, so I need a sum of angles, so I need to use the positive sign here. So it's going to be the sine of the first thing, sine of 120, times the cosine of the second thing, 45 degrees. Which sign was it? SIGN sign? I need a plus sign. Plus the cosine of 120 degrees times the sine of 45. And now what I've done is I've found four values in the formula that I can use that I know the values of because I have my unit circle. So sine of 120 degrees is square root of 3 over 2. Cosine of 45, that's square root of 2 over 2. Then I got my plus sign. Now cosine of 120, that's negative 1/2. And sine of 45 is square root of 2 over 2. And what I need to do at this point is just simplify. So when I multiply these together, I get square root of 6 divided by 4. Remember, you multiply fractions, numerators and denominators separately. And if I multiply negative 1 by square root of 2, I'm going to get minus square root of 2 over 4. And actually, I can make one fraction out of that because the denominators are the same. And there's my value of sine of 165 degrees exactly. Square root of 6 minus square root of 2 all over 4. All right, they want the cosine, so I can do the cosine of that sum of angles. 120 degrees plus 45 degrees. The cosine formula for a sum needed a minus sign between the two terms. And it's cosine of the first thing times cosine of the second thing minus sine of the first thing times sine of the second thing. And the good news is actually, I've already found these four values, I think. I think they're the ones I used in the sine formula. Let's see, cosine of 120 was a negative 1/2. Cosine of 45 was square root of 2 over 2. Got minus sine of 120, that's square root of 3 over 2. And sine of 45 is square root of 2 over 2. So multiplying these together again like I did, I'm going to get negative square root of 2 over 4 minus square root of 6 over 4. And I can make one fraction out of that, negative square root of 2 minus square root of 6 over 4. That's an okay place to stop, although I'd imagine the back of the book would pull that negative out of both terms and write it like the negative fraction. Like this. But if you got here, I'm pretty happy. Okay, and now I need to do the tangent. Now I do have options for the tangent. It's simply, I've already got the sine of the angle and the cosine of the angle. I could divide these two. But let me just go ahead and show you the actual use of the formula. So if I needed tangent of 120 plus 45, well, using the formula for the sum, that would be the tangent of 120 plus the tangent of 45. Cat's messing with the cabinets behind me, sorry. All divided by 1, and notice you need the minus sign here. Minus tangent of 120 times tangent of 45. So we need to know what tangent of 120 degrees is. And I know from working with a unit circle, I get negative square root of 3 for that. So tangent of 120 is negative square root of 3. Plus tangent of 45 is even nicer, that's 1. All over 1 minus the tangent of 120 times the tangent of 45. And I get negative square root of 3 plus 1 divided by 1 plus square root of 3. And that's not a bad place to stop. This is admittedly a little bit tougher in radians than in degrees. Maybe it helps to convert mentally or written out to degrees. But I'll tell you, I happen to know that pi over 12 is pi over 4 minus pi over 6. And you can check my math there if you need to. So let's see if we can get these out. So the sine of pi over 4 minus pi over 6 would be the same as the sine of the first angle times the cosine of the second minus, notice we're using the bottom sign now, the cosine of pi over 4 times the sine of pi over 6. And I can get those values there. Sine of pi over 4 is square root of 2 over 2. Cosine of pi over 6 is square root of 3 over 2. I've got minus, hey, the cosine of pi over 4 is square root of 2 over 2. And the sine of pi over 6 is a half. So I end up with something like square root of 6 over 4 minus square root of 2 over 4. Which is the same as square root of 6 minus square root of 2 all over 4. Cosine of pi over 4 minus pi over 6 would be the same as cosine of the first angle times cosine of the second angle. And notice this, the sign we need now, we need a plus sign. Plus the sine of pi over 4 times the sine of pi over 6. So I can get those values. We already got them actually. Cosine of pi over 4 is square root of 2 over 2. Cosine of pi over 6 is square root of 3 over 2. We got plus sine of pi over 4. Sine of pi over 4 is square root of 2 over 2. And sine of pi over 6 is a half. We're going to end up with square root of 6 over 4 plus square root of 2 over 4, which is square root of 6 plus square root of 2, all over 4. Okay, in the interest of time, I went ahead and wrote out the formula for the tangent, except I left this plus sign off here. And we'll note that tangent of pi over 4 is 1. Tangent of pi over 6 is square root of 3 over 3, and there's a reason why I showed you this one here. Then I've got 1 plus the product of 1 and square root of 3 over 3, and that's square root of 3 over 3. But the issue here is that I've got a complex fraction. So the way to deal with that would be to multiply everything top and bottom by a least common denominator, which is 3. So I'm going to get a better answer of 3 minus square root of 3 over 3 plus square root of 3. And again, I'm not super upset with a 1 radical left in the denominator here.